So if you missed lesson 3.2.6, or if you just need a little extra help with figuring out what the strongest intermolecular force present is for a molecule, then this lesson is for you. We're going to skip down to the description of what intermolecular forces are. So in order to do that, I want to sketch a quick picture of a water molecule. Water, H2O, has two bonds in it, and if you get water molecules together, they actually have a force of attraction between them. This is called the intermolecular force, IMF for short. So let's say you've got a big glass of water, okay, and it's a really hot summer day and the glass of water is heating up. The forces that are going to break are those intermolecular forces holding the water molecules together. So that way some of the water can turn into a vapor and fly away. You could also do this with a pan of water boiling on the stove. As you put energy into that water, the intermolecular forces between the molecules break and the liquid turns into a gas. Some forces for certain types of molecules are stronger than others. So let's start with the weakest. Dispersion forces are present in every single kind of molecule. So even nonpolar molecules slightly attract each other. That's because of the random movement of electrons. Some electrons in a molecule may accumulate a little bit more to one side temporarily, which in an adjacent molecule would repel the electrons away. So you'd have a slight partial negative and a slight partial positive, and that is called the dispersion force. So it takes a lot less energy to break a dispersion force than it does the force that we were talking about between water molecules. And there's a reason for that. Some molecules are polar, which means they already have a partial positive end and a partial negative end. Let's look at HCl, for example. Because there is a difference in electronegativity of greater than 0.5 between these two atoms, that means that the chlorine is going to have a partial negative charge. It's sucking electron cloud away from the hydrogen, leaving it with a partial positive. So you can see how the hydrogen of one molecule would be very attracted to the chlorine of the other. This is called the dipole-dipole force. The final type of intermolecular force is called hydrogen bonding, and that is when there is an extreme difference in electronegativity, like in a water molecule. Water is 3.44, hydrogen is 2.1, so this oxygen is really pulling on the electron cloud from these hydrogen atoms. So you're going to have a big partial negative and big partial positives, causing that force of attraction between two water molecules to be the largest. So, as part of the homework, you are supposed to draw each of these, describe the shape, clarify if it's polar or nonpolar, and then specify the type of intermolecular force present. So let's take a quick look at these. Water, for example, has this bent shape. I'm actually going to go to the answer key to talk through these. Be a little faster than me writing. Water has a bent shape, and to figure out if it's polar or not, you need to do a couple of things. First, you need to make sure to draw it in the correct shape. If I were to draw water in the linear shape, then it would look like the poles would cancel out, because you would draw an arrow going in and another arrow going in, and it would look like they cancel out. But that's just not the case, because water, since it is bent, that oxygen is pulling up on both of those hydrogens. And a little chart to help you with this, how to tell if something's polar or nonpolar. First, you have to ask yourself if it's got non-metal atoms, because those are the types of things that can form a covalent bond in the first place. And then there's that magic number. is there an electronegativity difference of 0.5 or more? If yes, you still don't know if it's polar for sure, because you've got to check and see if the arrows cancel out. If the arrows don't cancel out, then you've got a polar molecule. That means that there's a positive side and a negative side. Another helpful flowchart, how to identify the strongest type of intermolecular force. If something is nonpolar, it automatically has the weakest forces between molecules. But if something's polar, you have to ask yourself an additional question. Does it have a hydrogen bonded to an F, an O, or an N? If yes, that's the strongest type of intermolecular force possible, the hydrogen bonding force. And if it's polar, but it doesn't have the specific bond referenced above, then it's got medium forces, the dipole-dipole. So I'm also going to label on here weak, strong, medium. That's how much the molecules are held together. So back to this, the other examples here. The NF3 has the fluorines all pulling down, and this is definitely a polar bond because the difference between the two is greater than 0.5 if you look up nitrogen and fluorine's electronegativities. And so it is polar, but it doesn't have that hydrogen bonded to an F, an O, or an N, so it has dipole-dipole intermolecular forces. And the last one, you can see in my picture here that even though chlorine is more electronegative than carbon by a difference of 0.5 or greater, because one chlorine's pulling up, one's pulling down, one's pulling towards the left, one's pulling toward the right, they all cancel out. And so it ends up being nonpolar because there are no partial charges. So those molecules are only going to be weakly attracted to each other with the dispersion forces. So let's talk about evaporation. Which of the molecules would evaporate the slowest versus the fastest? Well, the ones that would evaporate the slowest are the ones that love each other the most, the ones that are most held together by the strongest forces, in which case this would be water from those three examples, because there are strong partial positives and partial negatives attracting one molecule to another. The opposite idea of that would be the CCl4. It would evaporate very fast because there are only weak forces holding the molecules together. There's a special rule called like dissolves like, meaning polar things dissolve in polar things. So this question is, which of the molecules would likely dissolve in water? Well, since water is polar, NF3 would also dissolve in water because it is also polar. Which substance would have a higher boiling point, something that's polar or nonpolar? Well, again, things that are polar have those partial charges, making them love each other and be very attracted to each other. So things that are polar would be harder to boil because you would require more energy to break those intermolecular forces. Number 5 wants you to rank these in order of the strength of the intermolecular forces. So the weakest here is CF4 because all of the poles cancel out, making that nonpolar with dispersion forces. The medium one would be OF2 because that one has dipole-dipole forces, the medium forces holding them together. And last but not least, HF would have hydrogen bonding, very strong intermolecular forces holding those together. Finally, explain why water is a liquid and hydrogen sulfide is a gas. Well, water is extremely polar, so the molecules love each other and the intermolecular forces are strong between them, attracting them together. It's not the case with H2S. That's nonpolar because the electronegativity difference between sulfur and hydrogen is not 0.5 or greater. In fact, if we look it up for sulfur, it is 2.58. So the difference here is only 0.48. So that is why that would be a gas. The forces are not strong holding these together, so it's easy to see why one could fly away from the other one. And that's it.